Hello, welcome to my video on data structures. In this video, we will discuss the implementation of hash table with separate chaining. We will first discuss the internal data storage for hash table implementing separate chaining. Then, we will discuss the implementation of several important operations. Here, we will make use of the myVector and myLinkList classes that have been implemented in modules 1 and 2 respectively. You can also try using the vector and list classes from the C++ standard template library. We first define a template class named hashedObject, which is used to bind the key and the value together. From lines 5 and 6, we can see that the key and value can take any types. The implementations of the big five, such as the constructor, destructor, and assignment operators, are omitted right here. The default behaviors of these functions will most likely do the job. Each hashed object is treated as a record and stored in the hash table. Now, let's take a look at the implementation of the hash table class. Recall that we can treat the internal storage of a hash table with separate chaining as a two-dimensional table. The first dimension is implemented using the myVector class. The second dimension is implemented using the myLinkList class. The records are stored in the linked lists. The myHashTable class contains three private data members. The first one, the size, is used to keep track of the number of records that are stored. The second one, declared in line 8, is the two-dimensional table we have discussed before. The first dimension of the table is a set of linked list pointers, and the second dimension consists of sets of hashed objects. The third data member contains a set of preloaded or precalculated prime numbers, which are used to facilitate the table doubling and table halving. Here is the constructor function. In line 4, note that the variable hashTable corresponds to an instance of the myVector class, and calling its resize function further calls its reserve function, which allocates sufficient memory to the vector. The variable initSize corresponds to the hash table size, or the maximum number of buckets the hash table can hold. Then, in line 7, we assign each bucket with the address of a new and empty linked list. Finally, in line 9, we set the size to 0, indicating that the hash table contains no record. Note the difference among the size and the capacity of the vector hash table. The variable the size declared in the myHashTable class corresponds to the number of records that are currently stored, while the size of the vector hash table corresponds to the number of buckets the hash table can hold. Note that each bucket can contain 0 or multiple records. And note that the ratio between the number of records and the number of buckets is the load factor of the hash table. Finally, the capacity of the vector hash table is not used here, so we can ignore it for now. Here is the destructor function. It simply collects the memory allocated for each individual bucket of the hash table. Note that the number of iterations we need to perform is the size of the vector hash table, which corresponds to the number of buckets in the hash table. Here is the search function, which we named as contains. It checks whether the record with the key is contained in the hash table. In line 5, we compute the hash value of the key using the universal hash function. We will talk about the universal hash function in the later sections of this module. For now, you can consider it as a simple modulo function. In line 6, we use a for loop to scan each record in the corresponding bucket. In line 8, we compare each record's key with the search key and return true if the keys match. We implement another form of the search function and name it as retrieve. In addition to telling whether the record exists, it also retrieves the corresponding information. If the record exists, it is stored in the second parameter, data. This is done with line 10 of the code. The other part of the code is identical to the previous contains function. Let's look at the insert function. In line 6, we need to check whether some existing records contain exactly the same key. If yes, we should not perform the insertion as the keys should be unique. We then compute the hash value for the record to be inserted in line 8. In line 9, we will simply append the record to the end of the bucket by calling the pushback function from the linked list. Finally, in line 11, we check whether the insertion will make the load factor larger than 1/2. If yes, we'll perform table doubling. For the remove function, we also first compute the hash value in line 6 and scan each record in the bucket in line 7. In line 11, we will call the erase function from the linked list to remove the record if we have found a key match. We will also check the load factor and invoke table halving if necessary. Otherwise, if the record to be deleted is not contained in the hash table, we will return false and do nothing. Now, let's take a look at the functions for table doubling and table halving. In lines 4 and 11, we use a function called nextPrime to compute the target hash table size after the table doubling or halving. Recall that the target size should be the smallest prime number that is larger than its parameter. Therefore, the nextPrime function is essentially a binary search algorithm applied to the set of preloaded primes. After computing the target size, we will call the rehash function. Here is the implementation of the rehash function, which contains 3 major components. First, we need to construct a new hash table with the target size. This is done by lines 5 through 7. Note that in line 5, the hash table is initialized with the target table size. Second, we use the new hash table to replace the old hash table, which is done with line 8. Note that the hash function unifhash implemented right here automatically takes the size of the hash table as the divisor of its modulo operation. In this case, the replacement of the hash table has implicitly updated the hash function. Finally, we will perform rehashing on each record with lines 9 through 11. Essentially, each record from the old hash table is inserted into the new hash table. Here, we use the move function to convert the record into R value, such that the rehashing will not incur additional memory usage. Okay, now let's try our implementation. The code block shown here tries to insert the data using the insert function. It will print whether the insertion is successful. Then, we will test the delete and search functions. As line 4 shows, for each of the record, there is a 20% chance that we will delete it from the hash table. If we delete a record, we will print out whether the deletion is successful, and if yes, which record is deleted. Then, we will try to retrieve the record from the hash table. If the record has been deleted, we would expect to see the retrieval failed warning. Otherwise, we would expect to see the corresponding information being printed. The testing data simply contains a set of people's ages, which are shown in the left panel here. The names are used as key, and the ages are used as value. From the output shown in the right panel, we can see that all records were properly inserted. The records of Chris and Hank were deleted, and they caused the expected retrieval failures. The other records were successfully retrieved. And by comparison, we verify that the retrieved information is identical to the input information. In summary, we have discussed the implementation and testing of hash table with separate chaining. In the next video, we will discuss a different way to handle hash table collision. The new way is called alternative probing. Thanks for watching and see you next time.